Let us proceed. Water. What's the chemical formula? H2O, which means? Two hydrogens, one oxygen in a single molecule. The molecule looks like Mickey Mouse. That big oxygen molecule in the middle, two little ears on the side, those are the two hydrogen atoms. Why do those atoms stick together? And the hydrogen atom has an electron cloud around the outside. That's negatively charged. The oxygen atom has an electron cloud. It's negatively charged. Why do these two negatively charged things stick together? They should be repelling each other. Why do they stick? Well, let me draw you the situation here. Hold on now. Let me get my pencil out. You know, days are a little different nowadays. My pencil has software running in it. When's the last time you had a pencil they had to reboot? So, let me see if I can draw the water molecule for you. Let's do a sketch, not that one. Let's go over here. Yeah, kill that. That's good. No, not that. Okay, fine. And let's see, here's an oxygen atom. And here's two hydrogen atoms. Looks like Mickey Mouse. And what I've drawn are the electron clouds. Now, why do these electron clouds stick to each other? Well, let's ask a different question. Where are the protons? Well, the protons are in here. There's one there and there's one there. There's a bunch of protons in here. Those protons are positively charged. Now, if you were an electron, where would you like to be in this situation? You want to be as close to all those positive charges as you can get, wouldn't you? Because you're attracted to positive charges. They turn you on. So, where would you want to be? Well, if you were an electron, you would like to be right here or right here. Now, you're not allowed to be there all the time. Sometimes you have to go around the outside and fulfill your duties to populate the electron cloud, but most of the time, you can sit right where it's nice and warm and comfortable between those two positive charges. And look what happens. You get a nice negative charge built there that's attracted to these two positive charges. You get a nice negative charge there that's attracted to those two positive charges, and the whole thing is stable. That's called a covalent bond. Covalent bond is nothing more than the electrons wanting to be between the positive charges and exerting just enough force to hold those positive charges in place. And you learn in high school that it's all about the shells and the 8 things, and they can be only 8 or 6 or whatever it is. All of that is true, of course, but the real reason is that the electrons just want to be there, and they attract everybody. So fine. Now, the water molecule is interesting because I can draw that line and notice that all the negative charge is on one side, or most of the negative charge is on one side. The bottom side there is mostly positive charge, or at least it's more positive than the other side, which means that the molecule has a dipole. It's negative on one side and a little more positive on the other side. Now, that's unique. Many molecules don't have that characteristic. Water does, and it's a very strong dipole. What that means is that when you sprinkle a little water on your hand, there's little electric charges on your hand, and all the water molecules will rotate so that the negative or positive side, whichever is attracted to them, will stick to your hand. This is what makes water wet. Water is wet because all the molecules rotate and stick to whatever they can. They're free to do that rotation, and they have the dipole. So, whoop, they slip in. This is also what makes water a very good solvent. Water can dissolve things because it'll rotate and stick to the molecules that have a slight positive or slight negative charge, and it will pull them along with them. Salt will dissolve in water this way. Other things, the sugar will dissolve in water this way. Lots of things do. This is why water is a good solvent. It's not hard to tear those hydrogen atoms off the oxygen atom. It only takes about 40 or 50 volts, probably about 40, right? So here's a nice little experiment you can do. If you have kids, the kids will love this. You get a glass of water, fill it up with water, get some 9-volt batteries. You know those 9-volt batteries? They have a little male and female thing at the top, right? So they look like rectangles, and there's a little female thing and a little male thing. And then you get another one, put it right here, and you put the female part there and the male part there, and then you get another one, and you put the female part there and the male part there, and you get another one, and another one, and you get 5 of them. Now that's 9 volts times 5, that's 45 volts, that's plenty. And you just stick them together, they'll stick and be nice. You get a couple of wires. You take a couple of wires, you dip them into the glass of water. Don't let them touch. Just let them hang out there. Put a little salt in the water. That helps. A little salt. And what you will find is that bubbles will form around those 2 wires. On one side, you'll get oxygen, and the other side, you'll get hydrogen. You could actually collect it if you wanted to like collect it in balloons, but you don't have to. Just let it kind of sit there and bubble and fizz. If the glass has enough of a lip on it, then the oxygen and the hydrogen will collect in that part of the glass. Now the hydrogen wants to rise, it will escape, but some of it will stay behind. You can let it fizz for about a minute and then walk up with a match and get a little explosion. Not a big one, but it's cool because you get your kids to watch and look at it's bubbling, kids. Oh, now watch this. If you do that long enough, and by long, I mean about 5 minutes, you will find that the glass of water has gotten pretty hot. It takes a lot of power to rip those hydrogens off that oxygen. The batteries will be pretty well depleted. You will have used most of those batteries up. And if you were very careful, you would note that the density of that water was just a little too high. Not much. Just a little too high. Water is usually 1 gram per cubic centimeter. But now it will be just a little more than 1 gram per cubic centimeter. And the reason behind that is that heavy water, water that has 1 extra neutron in its hydrogens, does not want to get ripped apart quite as much as regular hydrogen does, regular atoms do. So you will find that your water glass is slightly enriched in heavy water. Now, the Atomic Energy Commission is not going to come by. You don't have to worry about that. However, if you want to buy about 10,000 batteries and repeat that experiment over and over and over again with the same glass of water, you could get rid of all of the normal water and have nothing but a glass of heavy water. That would be expensive and not what I'm supposed to talk about. So let's actually talk about what I'm here for. This is just going to be a fun talk. Not a lot of technology. I'm not going to put code on the screen, although I am going to talk about programming and programmers. And I'll be talking a little bit about the past. Actually, I'll talk a lot about the past and a little bit about the future. If you look around the room, you will find that there is a certain imbalance in this room. There's more of one kind of people than there are of another kind of people. Specifically, I'm going for the type of chromosomes you have. There are an awful lot of Y chromosomes in here, too many, and not quite enough X chromosomes. Right? Now, why is this? Although the ratio in this room is actually pretty good. But why is this? What's going on in our industry that would concentrate males into programming and not concentrate females? By the way, that's the opposite of how it used to be. In the 50s, there were more women programmers than men programmers. In the 60s, it was pretty even. When I got my first job, I got a job at a place where they had a couple of dozen programmers, and about a third to a half of them were women. But 10 years later, the ratios had completely changed. And today, in the Western world, the ratios are horrible. It's about 3% women. What is going on? Now, I don't have an answer to that question. I'm not here to try and answer that question. I just think it's awfully interesting. There must be some process at work. And some folks think that process is nefarious, and other people think the process is natural. I just don't know what the process is. But something is at work to keep that ratio the way it is. I don't think that's stable. I think it will probably have to change for reasons that I am about to discuss. Let's go back to the earliest days of programming, right? 1946. There was, in those days, one programmer. And I think I can tell you who that was. I think it was that guy. Alan Turing, interesting dude, wrote this paper in 1936 answering some esoteric mathematical problem. I won't bore you with what it was, except to say that in order to answer this esoteric mathematical problem, he had to invent the modern digital computer. Now, he did this by assuming that it was a device that could make marks on tape, and he didn't think it was electronic, and he didn't think it was even automatic. He thought that a person would be operating it according to very strict rules, but it doesn't matter. He invented what we would think of today as a modern computer. And has anybody read his paper? You have. Anybody else? This is a very difficult paper to get through. It's very, very thick. And so I advise you to get a book. And I think I have the slide for this book. Let's see if I do. No, I don't. Okay. The name of the book is The Annotated Turing. It's written by Charles Petzold. Charles Petzold's name you may remember. He was the guy who wrote all the MFC books, the Microsoft Foundation class books back in the 80s and 90s. And he eventually decided to stop writing software pornography and actually write some real good history of software. And he wrote the Annotated Turing. The Annotated Turing reproduces Alan Turing's entire paper, but it does so in little snippets. And it surrounds each of those snippets with the history and the explanation and what was going on and how it affected Turing. It's a fascinating book to read. I've read it twice. I'm going to read it again. It's a very, very good read, and it will give you a deep insight into the very beginnings of this industry that we're all in. How many of you are programmers? You see, that's most of you. What are the rest of you? We got some testers in the room. We got testers, how about we have certified Scrum Masters in the room? Oh, look at that. We got CSMs in the room. That's great. Yeah. So, Turing had invented this device in his paper. It got him interested in the whole automatic mathematics thing, the computational mathematics. He got recruited by the war effort and used his knowledge to help make machines that broke the German Enigma codes. We could say that Alan Turing won World War II, or at least was a big contributor to that. The kinds of equipment he was using looked like this. This is a relay. Anybody played with a relay? Relays are fun. They're real simple to understand, right? This is an electromagnet, just a coil of wire. If you run a current through the coil of wire, it magnetizes that piece of metal. This other piece of metal then snaps towards it, and that drives this little lever system that changes the position of these switches. And the switches might close or they might open, depends. If you think about that enough, you'll realize that's enough to do computation. What does it take to do computation? What operations are necessary to build a computer? Necessary and complete. You only need two operations to make a computer, to do anything. Negation and either and or. Doesn't matter which it is, and or, doesn't matter. Negation and or. You can get negation out of a relay just by opening a contact when you energize the coil. You can get ands and ors out of electric circuits just by wiring them together. You can build a computer out of relays. And he did. They built these very interesting computers that searched through the solutions for the Enigma code. But a relay is slow. How many operations can you get out of a relay? Well, 10 per second. So imagine a computer that has a clock rate of 10 hertz. Faster than you can think, but still pretty slow. Vacuum tubes had been invented, and they thought about using them. A vacuum tube would be 100,000 times faster. But they were really unreliable in those days. They weren't being mass-produced in any quantity. They weren't being reliably produced. They drew a lot of power. They failed a lot. They leaked a lot. So they couldn't make anything very reliable out of vacuum tubes. A vacuum tube could be used reliably in a circuit that had 1 or 2 tubes in it. But if you had to put 100 tubes in it, you knew that they were going to fail. So they didn't want to do that until a little later. Now, it wasn't too much longer. The war had been won by this time. But they started to build these vacuum tube machines. And this one is the automated computing engine. This is the first computer ever made, or at least some people think it's the first computer ever made. There's some doubt about that. But it was certainly one of the first electronic computers ever. It was a von Neumann machine. It was programmable. It had memory. It used vacuum tubes, so it was relatively fast. The memory looked like this. It was mercury delay lines. There's a big long tube of mercury, and you put a speaker at one end, and you pump bits into that speaker, and those sound waves move through the mercury at a pretty high rate of speed, and you put a microphone at the other end, and then you capture that electronically and wrap it around to the beginning. So this is rotating memory, kind of like a disk, except it's moving through the mercury. The memory was in the mercury. And they made that work. They got that working. This computer had 1024 words of 22 bits. They didn't know about bytes. They were just trying to store bits. And it worked. It was fine, except that every time a truck went by, it shook the mercury and messed everything up. So they had to eventually stop using mercury delay lines, and they fell back on this approach. And this approach is a cathode ray tube. Who's seen a cathode ray tube? Really? An old TV set? Anybody remember old TV sets? You turn them off and they didn't go off? The picture just kind of collapsed slowly, until you were just staring at that eye, Why did that happen? Well, it's because the cathode ray tube had a filament at the back end, and that filament would throw off electrons. And the electrons would move forward towards the front of the tube where there were phosphors, and the phosphors would glow. You turn off the tube, you turn off the TV, but the filament's still hot. It takes a long time to cool down. It's still throwing off electrons, and you still get that little spot, until finally the filament cools all the way down. The other thing about a cathode ray tube is that they used these plates. They put voltages or currents through these plates, and they could move the beam. So they could sweep the beam across the tube. That's why televisions work, by the way. But the nice thing about the beam is that it would deplete the charge on the screen wherever the beam hit. And then the next time you swept that, you could tell by the current density in the beam whether the beam had been there previously. So it was a kind of memory. The tube remembered where the beam had been. And so this became the memory of the automated computing engine. It also became the primary output device. People would read the results of their programs by looking at the bits in memory. This was memory you could actually see. That was the output device. And Alan Turing would write programs and then read the results on the screen of the memory device. Now, what was writing code on this machine like? Well, there wasn't an assembler. He didn't have any language at all. He had to write it all in binary. Has anybody written code in binary? This is fun, right? I've done this. You can do it. You have to translate all the instructions into binary. He used base 32, by the way. He grouped his bits into groupings of 5. And then he would write it all down, and then he would be able to get those bits into memory using a paper tape reader. He had to do all of the the address arithmetic by hand. So he had to know what addresses he was jumping to and what addresses he was reading from and writing to and so on. And all that address arithmetic had to be done by hand. It had to be done perfectly. If you added an instruction, it changed all the addresses. So you had to go back and change them all. Very time-consuming, very deep, detailed work. And yet he wrote a lot of code and executed a lot of code. And the kind of code that he wrote was the kind of stuff that you and I hope we never have to write. The folks who made this computer did not know that anybody would want to call a subroutine. The idea of a subroutine hadn't really even been thought of. So there was no stack, and there was no way to capture a return address. Alan Turing had to invent that concept. And he had to invent the concept of a stack, and he had to write the code that would implement a stack of return addresses. And he had to do that, of course, in binary. He wanted to do math in real numbers, but of course a computer only deals with integers, so he had to write a floating point package in binary. Has anybody written a floating point package? Go home and do this. This is fun. All right, so this is a weekend exercise. Get rid of the family. You're going to disappear down in the basement. No one's going to hear from you for 2 days. And go down in the basement and write the code. You can do it in Java if you wish. Just don't use floating point numbers. Use integers. And write the code that will add 2 floating point numbers together. And you'll find it's a very interesting challenge. There's all kinds of crap you've got to do to line those numbers up and do the exponent subtraction, all this stuff. He was doing this in binary, right? So that's pretty cool. He did a whole bunch of other stuff like that. He wanted to do long calculations, which he managed to do over the year or so that he worked. And then he wrote a document about his experience. And I've drawn a few quotes from this document because they're remarkable quotes. First of all, he said, a year later, "We shall need a great number," a great number, we'll talk about that in a minute, "of mathematicians of ability." Are you mathematicians of ability? Is that what you are? Because there will probably be a good deal of work of this kind to be done. How did he know? How did he know that there was going to be so much work to be done? I think if Alan Turing were alive today, he'd be astounded at just how much work of this kind has been done. I mean, Angry Birds after all. But he knew even then that they were going to need a lot of people to write this code. And he called them mathematicians of ability because he recognized that this was not easy stuff. This was hard. Mathematicians of ability, that's what we're going to need. He went on to say, "One of our difficulties," and boy, did he nail that one right, "will be the maintenance of an appropriate discipline so that we do not lose track of what we're doing." Now, there sounds like the voice of experience to me. I think he lost track of what he was doing 1 or 2 times and came up with a few disciplines to use. Have you ever lost track of what you were doing? Writing code? Yeah, have you ever stared at the screen and gone, what the hell did I just write? The maintenance of an appropriate discipline. What could that discipline be? Well, we need to go forward. So, mathematicians of ability, a great number, appropriate discipline. Keep those concepts in mind as we move forward in time. The number of computers in the world is now on the order of 1. There was a time when there was just 1. And I'll use big O notation so that I've got room for slush, right? But on the order of 1, the number of programmers in the world was on the order of 1. There was a time when there was 1 programmer in the world. And the date we're pretty sure of, 1945, 1946, somewhere around then. Now that's not that long ago. That's 73 years ago. Is that right? 73, 74, something like that. It's not that long ago. Less than a person's lifetime ago, there was 1 programmer in the world. How many programmers are there now? Well, think about that for a while. We'll come back to that question. The problem of memory was pretty significant. Cathode ray tubes couldn't store enough bits. So we stumbled upon this idea. Now, this is a core plane that I own. This is core memory. I own this core plane. I bought it when I was 16 years old. Actually, a friend of mine bought it, and I bought it from him recently. He actually gave it to me. But I have this at home. This is a micrograph of the same structure. I took this micrograph. This is a core plane. These little rings are ferrite. Ferrite is powdered iron and clay that has been baked. Now, it's powdered iron, so it's magnetic, and it's clay so that you can get this shape. and then you weave them into this network of wires. Now, why? Well, if you run current through these wires, if you run just the right amount of current through these wires, you can magnetize one of the rings. If you run too little current through the wires, the rings don't magnetize. But if you run just the right amount through, they do. So what they would do is they would run half the necessary current through that wire and half the necessary current through that wire, and that would be enough to magnetize that ring and none of the others. And so they could flip the magnetic state of a ring. It could be now north-south or south-north. 2 states, 1 bit. And that's how we would store our bits in memory. How do you read this? Well, you take a bit, you take one of these rings and you flip it. You presume that it is a 1, you don't know its state. You write it to 0. If it was a 1, it will flip. As it flips, it induces a current on another one of these wires in here. And you read that with a little amplifier. If it didn't flip, it doesn't induce that current. That's really hard to read, by the way. But they tuned it all, they got it all working. And core memory became the way that memory was stored in computers between, the late 40s all the way into the 70s. Core memory. I worked on a lot of core machines. Who worked on some core machines here? Anybody work with core? Nobody worked with core. Core memory was great. You turn the computer off, all that magnetized cores, they stayed. They kept their magnetism. You turn the computer on, everything was still in memory. We used to load the operating system up into memory and then turn the computer off. Then turn it on later, it'd still all be there. We'd put our programs in there, turn it off. They'd stay there for weeks, right? Because the cores did not get unmagnetized. But those cores were expensive. Think about making that. Now these little rings, they're about 1 millimeter in diameter. And those are big for core memory. There were a lot of cores that were smaller than that. How do you make that? Well, you'd put it on a loom, of course, but you still need people to thread those wires. And a lot of people, very labor intensive. Core memory cost more than $1 per bit. Memory was really expensive in those days, $1 a bit. Who's got a thumb drive in their pocket right now that's got, 16 gigabytes? 16 gigabytes, what is that? 64 gigabits? Yeah, 16 gigabytes would be 64 gigabits, $64 billion worth of memory. You and I do not understand just how rich we are. And I mean that very literally. We are overflowing with memory. Memory is just everywhere. We have wealth beyond our dreams in memory. You and I, we don't even think about memory anymore. Anybody think about how they're going to fit it all in memory? How are we going to fit this all? Who cares? Well, how much you got in your machine? I got 16 gigabytes in my machine. Who cares anymore? We spend it like, we're going out of style. The other thing we spend are cycles. Nobody thinks about that anymore. We used to count cycles. We used to count the number of instructions. There's a microsecond, there's a microsecond, that's 2 microseconds. We do all that math. We don't care anymore. We don't worry about it at all. In fact, who's using Java? Who's using C#? Okay, both of these languages run on virtual machines. What does that mean, virtual machine? It means that the machine has a simulator inside that pretends to be another computer. And it interprets the code as though it were this other computer. So it's burning cycles like crazy just to walk through this code. Now, I know there's jitting compilers and stuff like that, and they solve that problem. On the other hand, if you had told me 30 years ago that the majority of the world would be running their enterprise systems on virtual machines, I would have said you were insane. Nobody would do a thing like that. It'd be way too slow. It's not anymore. Our machines are stupidly fast, absurdly fast, and the machines are stupidly cheap. How many are doing it in the cloud now? Just spin up another server. Oh, I need 80 servers for that one. Okay, well, Amazon's got plenty. This is a different world, right, than I grew up in. But by now, it's the 50s. Core memory is being used. Vacuum tubes have become pretty reliable. They're mass-produced in quantity. It looks like it's possible that we could build computers out of vacuum tubes reliably. and we could build lots of them. And so IBM started to build them. There were a few in place by the time Fortran was invented. Anybody working Fortran here? Oh yeah, look at that, got Fortran. Good, good. Okay, couple of Fortran guys. Fortran was invented the year after I was born. I am older than Fortran by a year. This is Fortran. This little code here, just to give you an idea of how primitive this language is. This if statement here, oh yes, we had if statements. This if statement says, well, if the quantity IB plus IC minus IA is negative, then jump to line 777. If it's 0, jump to line 777. If it's positive, jump to line 799. That was an if statement. That was the only if statement in early Fortran. And the line numbers, you see the line numbers up there? You'll notice that they're not necessarily in order because they weren't actually line numbers. They were just labels, arbitrary numbers that you could stick on a line. They did not have to be in order. They never were in order. They were just names for those lines. A line did not have to have a number. You can see that one if statement up there doesn't have a number. You don't have to have a number on a line. You can if you want to, but if you're going to jump to it, you need a number. Now, why would they use numbers instead of names? Because numbers take less memory than names. Names take bytes. Numbers take maybe 2 bytes a word. And the language was designed to fit in these very small machines. The C here is a comment. All right, and notice that the C's all line up in a particular column. That column was reserved. First column was reserved for comments. Right? You couldn't put anything in that column except a C. I don't know why they thought that was a good idea, but they did. When we wrote this code, we did not write it by typing it. Programmers did not know how to type in those days. They had no keyboard skills. There were no keyboards for them to use. Right? We wrote our code on paper with pencils. This is a standard coding form that we might have used. You'll notice it has 80 columns and about 30 rows. And we would write our code in black number 2 pencil. Our editor was an eraser. And we would very carefully write this code and then execute it in our brains over and over again, looking for any flaw that we could think of. And by the time we were done and we had thought, okay, we're done with this, this code is probably going to work, it was still in paper. So we had to walk it down the hall to a room where there were key punch operators. The key punch operators were operating key punch machines. Now in these days, anything that went into a computer went in on cards. You didn't type things into a computer. You didn't read things in from tape. Anything that went into the computer went in on cards and came out either on cards or on a printer. Everything went in on cards. That means if you were doing payroll, you had a bunch of data you needed to get into the computer. Somebody had to punch that. If you were doing inventory, you had a bunch of data that had to go in. Somebody had to punch that. So there were people who would gather that data, write it all down on sheets of paper, hand it to the key punch operators. Key punch operators were madly punching cards. Those cards would then go to the computer. The programmers would walk into that room, and these people were busy. And they're punching, punching, punching like crazy. The programmer would walk into that room, and all the key punch operators would stare and glare at them because we're adding more work. First key punch operator I ever saw. I walked into that room, young programmer, 18 years old. I had a little sheaf of paper. I wanted them to please punch it. And one of the key punch operators looked up at me and with anger in her eyes, she said, "Flutter away, little butterfly." So I ran out of that room with my tail between my legs and I went down into the basement. I found a key punch machine. I taught myself to type. I never went back in that room again. Many programmers, however, used the key punch operators. They would walk in the room and they would toss their paper into the basket. And eventually, usually a day or two later, the key punch operators would get to it and you could go and get your deck of cards. Now, the key punch machine would punch in, you can see it up here. There's the cards up there. You can see the little holes, but very at the top of the card, you'll see that there's a little bit of code written up there. There's a dot matrix printer in the key punch that would print on the card what the card contained. So you could get your box of cards and you could go through it and read the code by looking at the top of the cards. And you'd better too, because the key punch operators did not punch accurately. They had no idea what they were punching. They weren't programmers. So you would walk through there, make sure they punched everything. They didn't, so you'd have to fix a few cards, and we had a key punch machine in the room for us to fix it. Eventually, you got the deck into a state where you thought it was acceptable. You put a rubber band around it, you write your name on the top, draw a diagonal line across the top in case you drop it. And then if you drop it, all you have to do is get that line to line up again. Take it down the hall to the machine room. Programmers were not allowed in the machine room. Programmers never touched the computer, right? Only operators were allowed in the machine room. Operators were a different species of human. They had complete domain. There was a lock on the door. Only they had the key to that lock. You wanted to compile your code, you went up to that machine room door and you made the necessary gestures of obeisance, and then you put your deck in the basket and you walked away. And then an arm would reach out from behind the door and take that deck into the bowels of the machine room, where it would sit until 3 in the morning. It would sit there until 3 in the morning because that machine was busy. It had to run 24 hours a day. It had to run 24/7. The machine is a $10 million machine in the 1960s. So a minute of idle time was a disaster. So those operators were running bills of material and inventory and payroll and every other batch job they could until 3 in the morning. 3 in the morning, all the jobs are done. They stacked up all the programmers' compiles on the card reader, pushed the read button, and they went and had coffee. All the compiles would run. They'd print off. They'd take those print-offs. They'd tear them off. They'd put them on a table outside the machine room. You came back the next day. Maybe your job had been done. Maybe your compile had been run. You went to the table. Oh, there's my thing. It says Martin on the top. You take your listing and the deck of cards. You go back to your desk. You open it up and realize that you had forgotten a comma. This was your life. In order to get productive, a programmer would have to work on 5, 6, 7 programs at the same time. You'd get one ready and put it in the basket. You'd get the next one ready, put it in the basket. You'd had to have a whole bunch of them going in order to be anywhere near productive. This was the era that Lisp was invented. Who's written some Lisp? Oh, look at that. We got some Lispers in the room. 1950 what? 8. Lisp was made. Lisp is the language that will not die. We have tried to kill it many times. It keeps coming back. It's like the cat, right? That keeps coming back the very next day. Lisp will not go away. Because of that, I now believe it will be the final language. Once we have finally settled everything out, only one language will be left. It will be Lisp. All programmers will be writing Lisp eventually. It's not the case today, probably will be one day. But that was the beginning of functional programming. Functional programming began in 1958. It actually began in 1936 when predicate calculus was invented, but the first programming language to do functional programming was 1958. You may think that's a modern concept. It's not. Between 1954 and 1960, IBM sold 140 of these 705, 709 species of computer. These were monster machines. In size and in expense. As far as power, they were like minuscule, right? My AirPods have much more computing power than that machine did. But in the day, it was a pretty good machine. They were horrifically expensive. They were vacuum tube machines. They were very difficult, very unreliable. If you jumped on the floor, you could shake those tube filaments and get them to misbehave. So it was a very difficult time for computers. And they were horribly expensive. They were $1 million machines. IBM did not sell computers in those days. They rented them. And the rental price was enormous. IBM kept the capital value. They would just rent them out. And this was the era of Fortran and Lisp and Cobol and a bunch of other languages. This is also the era where programmers were mostly women, or at least they started out as mostly women and gradually transitioned to about 50-50 men and women. One of the original programmers was Grace Hopper. This is Grace Hopper. Grace Hopper, who was in the Navy, she was eventually a Commodore. She got involved with computing very early. She is the first person to realize that a human-like language could be used to program a computer. She called it a compiler. She coined the term compiler. She also wrote the very first compiler, which was a language called A0 that no one knows today. Eventually, she became instrumental in the primary driver of another language called Cobol for her sins. Anybody done Cobol here? Sorry about that. Awful thing to have had to experience. I'm glad you survived the effort. Cobol was a moral good and an implementation disaster. The moral good was that the idea of a language that could almost read like English was a great idea. It just doesn't work in software. So it was a failed idea, but it was a grand vision. It doesn't mean it wasn't a popular language. It was a wildly popular language for about 30 years, but it was not a great language in any sense. These were the programmers of the ENIAC, the computer at Princeton. This was not a stored program computer. This was programmed by plugging cords into slots and panels. And these were the programmers. It was all done by women. And by the way, programming this machine was no mean feat. You had to have a heck of an engineering sense to figure out all the timing pulses and the math and how to do this and that. So fascinating. Why were they women, by the way? Men built the machines. Women programmed the machines. It was a definite divide in labor. And programming at that time was considered clerical work. That changed later. But back then, it was clerical work, and so it fit within the mindset that women were able to do. It was much more technical than it is today. By 1960, the number of programmers in the world, the number of computers in the world was on the order of 100. Think about that, you know. In the 1960s, not that long ago, you know, flower power and hippies and Vietnam War and stuff like that, maybe there are 100 computers in the world, maybe 200, maybe 300, but it's on the order of hundreds of computers, not thousands. I went to the University of Illinois with my father. He was a science teacher. And we looked at the computer lab at the University of Illinois in the early 60s, and they were building a new computer there, the ILIAC 4. And the guy who was building it was very proud of it. And he said to this group of people that I was in, he said, "When this machine is finished, the computing power in the world will double." Which says an awful lot about how much computing power there was in the world. Number of programmers was about 10 times larger than the number of computers. Now why? Well, because in those days, in order to keep a computer running, and you had to keep it running 24/7, in order to keep it running, you had to load it full of code. And any code that ran was code that you wrote. There were no libraries, there were no frameworks, there was nothing you could download, no little cute things that would run, no operating systems, right? It was literally hard metal, empty memory, and if you ran something in it, you wrote what ran. So it took a lot of programmers to do that. About 10 times the number of machines. 10 programmers per machine is about the right number. But the world was about to change. Now, who were these programmers? These early programmers, the very first programmers writing all this code. Who were they? This thousands of people. There were no computer curricula at school. You could not go to university to learn how to program. The universities didn't even have any computers in those days. Or maybe one or two did, but hardly any did, right? And there were no courses you could take. So how did you learn to be a programmer? And in those days, what happened is that the companies who owned computers went to their employees and said, "Who wants to learn how to do this?" And a few people who were technically minded, scientists, mathematicians, engineers, would raise their hands and say, "Yeah, I'll take a stab at this." These were not young people. These were old people. They were in their 30s and 40s and 50s. They were mature. They'd been in the business for a while. They understood the business they were in, and they were thinking that this would be an interesting opportunity. These were not graduates. They were mature. The earliest programmers were old. Keep that in mind. But the world was changing fast. The transistor had been invented. The transistor completely replaced the vacuum tube almost overnight. And the computers that used to be big and power hungry and expensive suddenly got small and power efficient and cheap. and the numbers of them could rise enormously. By 1965, IBM was making 1401 computers by the tens of thousands. And these were cheap machines. They look still big, but that's much smaller than they used to be. The one big thing here, look at that sucker right there. That's a disk. Right? Now that disk has platters that are 3 feet in diameter. The platters themselves are about 1/2 inch thick. They weigh a good 500 pounds per platter. You'd have about 14 platters in that thing, right? And when you turned it on, they had a beefy motor in there to spin that sucker up. It would sound like a jet engine going off, and the floor would shake and everything, and then it would all settle down as all the resonances had been damped for just the right frequency. And that thing would sit there humming. All those disks spinning like crazy. They had like 4 or 5 seek arms around the outside. They were driven by compressed air. Had a seek time of about 1/2 second, but they'd have a whole bunch of those arms around the outside. Maybe you could put, 5 megabytes on that thing, maybe, right? I worked in a computer office once where it had one of those, and we were in the computer room, and we looked down at the floor, and little metal filings were coming out from the disk drive. We called the maintenance guy over, because in those days you had a permanent maintenance guy on staff all the time. Called the maintenance guy over, said, is that normal? And the blood drained from his face, and he hit the power button. He said, no. The disc, the spindle was carried on mercury bearings. One of the mercury bearings had dried up, right? And this thing was grinding the axle. He said, a couple of those things have cut loose, they'll go right through a concrete brick wall. So he's glad he turned it off. These machines rented for $2,500 a month in 1965 dollars, right? That's about $20,000 a month today. But that was in reach of a whole bunch of companies. And so now it was possible for thousands of companies to have computers in their buildings. And of course, they could write payrolls and build some material and inventory and general ledger code. They had to have programmers, though. The number of programmers, the number of computers in the world shot up. Now it's on the order of tens of thousands. The number of programmers went up too, and it went up by a factor of 10. Now there had to be hundreds of thousands of programmers in the world just to serve those machines. Who were they? Who were these hundreds of thousands? Now, it's only been 20 years. It's only been 20 years, and we're already at this phase where there's 100,000 programmers in the world. I'm 13 years old at this point. I've actually written my first lines of code. Right? I've actually played with the concepts of computers. I knew I wanted to be a programmer by this time. Right? There are 100,000 computer programmers in the whole world. Who were they? Well, there weren't enough engineers and scientists and mathematicians, and there still weren't graduates coming out of a university. So the programmers had to still be drawn from employees, but now it couldn't be the best and brightest, it had to be the next tier down. Still bright, still intelligent, accountants, planners, marketing people, whoever had a technical bent. The business had to have programmers. They had to have these programmers. So they would train them. They wrote aptitude tests. Does anybody remember the era of the aptitude test to see if you had the aptitude for being a programmer? This was a terrible time in life because you'd have to answer all these stupid questions and then there would be a binary result at the end. No, you're not a programmer, or yes, you are. Well, that's just dumb. Now, nowadays we know that programmers come in at least 2 different varieties. So programmers needed to be drawn from existing employees, and once again, these were older people. They were people who'd been around, they'd been in the business for a while. They might not have been brilliant scientists, but they were at least brilliant people. They were still old. Though not mathematicians, they were experienced, disciplined professionals. They had been in the business for at least a decade. They'd been around. They understood what projects were. They understood what the business was. They knew how to talk to management. They were not 22-year-old kids coming out of school. Very different from what we see now. By 1966, IBM was producing 1,000 IBM 360s every month. I worked on a number of these machines back in those days. They were gorgeous machines, beautiful things to work on. Very reliable, very fast. There was something really solid about working on an IBM 360. Very, very reliable machines. And they were making them in huge quantities, thousands of them every month. This was a fascinating era. In 1966, Ole Johan Dahl and Christian Nygaard, working at the university in Oslo, invented object-oriented design. Object-oriented languages were born in the mid-60s. They built a language called Simula 67, based on Algol. OO got its birth in 66. In 1968, Edsger Dijkstra wrote the famous paper that said GoTo might be considered harmful, and structured programming was born. And we already saw that functional programming had been born a few years before that with Lisp. In 1968, Ken Thompson and Dennis Ritchie go onto the 7th floor of the AT&T building, the Bell Labs, and they invent two things in a matter of a couple of weeks. They invent C and they invent Unix, and they changed the world. They were not told to do this, they just had a need. And they filled that need by inventing two landmark pieces of software. By 1970, Digital Equipment Corporation is producing 50,000 PDP-8s. These are little tiny machines, a desktop machine. It would sit about the size of that podium right there, right? Tiny little machines. This thing would be maybe $20,000. Here's one, PDP-8S, that was $10,000. It had a 48 microsecond add time. Right? Had 4K of core. My friend and I in high school, we would sit and we would look at catalogs of computers. We would look at catalogs with PDPSs in them and dream about how we could get $10,000. We didn't get $10,000. But we did go to the digital sales office and play with their computers there. By 1970, the number of computers in the world is on the order of hundreds of thousands. Now there's a lot of computers around. Now, hundreds of thousands of machines. How many programmers are there? Well, still a factor of 10 more, about 1 million programmers. 1970, maybe there's 1 million programmers in the world. It has only been 25 years. Maybe there's 1 million programmers in the world. Who were they? Hundreds of thousands of computers, 1 million programmers. Well, I was one of them. That's me at the age of 18. I was already working as a programmer. Never went to college for it. Never had to. Always had a job. Never had an issue. Nobody cared. Actually, not many people care today. How many of you taught yourself to program? Okay, that's a good half of you. Taught yourself to program. Then you went to school probably. I don't know if you thought the school was useful. A lot of people come out of school thinking, well, it's great to be there. Didn't really learn much. You may have learned something, I don't know. But even today, the college curricula for computer science is not driven by experience. How many of you went to school and came out and went into industry and got a real culture shock? Like, whoa, I didn't think it was like this. College is supposed to prepare you for industry. So far, they're not doing a great job of that. Tens of thousands of new CS and EE grads poured out of the universities. By now, there were university programs for learning how to program, and the universities were cranking them out in enormous numbers. Tens of thousands. They all had something in common. They were all young, and for some reason, they were almost all male. There was some demographic change that happened. It happened in the universities. Don't know why, but the grads coming out were almost all male. At my first job, there was maybe a couple of dozen programmers, most of them in their 30s or 40s. Half of them were women. Look at the age difference and the gender difference. Right? They were older, and they were about half and half men and women, roughly. 10 years later, I'm working at a different company. Maybe 50 programmers there, all of us in our 20s or early 30s, 3 were women. That's just my experience of that era. Something happened right then. Think it was in the colleges, don't know for sure. But the people coming out of university programs were primarily male, and they were stupidly young. Here's the graph. It's a fascinating graph of women in STEM fields. The blue lines are women graduates coming out of university in STEM fields. The red line is computer science. What the hell happened? And it shows this happened sometime in the 80s. I think it actually happened much earlier, because my experience was the number of women dropped in the mid-70s. So, don't know, but that's a fascinating curve. Don't know what did that. But no matter what happened, businesses had to have programmers. And what very young men lack in discipline, they make up for with energy. Anybody here work overtime on a project? Like, you know, more than 40 hours a week? Or 50? Who's got the record in here? Who's done a 50-er? Hey? Oh, look at that. Oh, yeah. How about a 60? Anybody? And see, notice we know. We know, because we wear that number on our shirt. I'm a 60-er. Who did a 70? Come on. Somebody did a 70-hour week in here. Oh, look, we got a few of those. How about an 80? We got an 80-er? Nobody did an 80-hour week except me. I was the idiot. What young men lack in discipline, they make up for in energy, and they're dirt cheap. You can hire them for a song. When I got my first job as a programmer, I was making $6,800 a year. I thought it was a fortune. It was enough for my car payment, and I could still live at home. It was a great time for me. Cheap, energetic labor. Now remember, up to this time, programmers were disciplined professionals. Right? The early programmers were not these young kids. They were disciplined professionals. They were older. They didn't need a lot of management or process. They knew how to manage their time, communicate, and work together. They'd gone through the whole problem of figuring out how to work at a company. They understood deadlines and commitments. You know, the old Rod Job Seeger song, right? What to leave in and who to leave out. They understood all that stuff. They were mature, older people. And they did miracles. Those early programmers were the ones who built the IBM 360 virtual memory system and sent us to the moon and did Apollo and Gemini and came up with structured programming and functional programming and object-oriented programming. These are the folks who came up with Fortran and Cobol, Algol, Lisp, C, and Unix, all these things that you and I would depend upon now. That was done by those early programmers, the older ones, the disciplined ones, the mathematicians of ability, the original programmers who knew how to get big things done. But now, if you were to look at those guys and see how they worked, what you would notice is that they were doing something that we would call Agile today. How many of you are Agile? I know this is the Agile thing, right? I'm at the Agile conference or something like that. Okay. They were too. Although they didn't call it Agile. But they worked in short cycles. They measured their progress. The programmers on the Mercury space capsule wrote their unit tests in the morning and made them pass in the afternoon. A kind of strange, kind of test-driven development. But all those concepts were there. They were invented by those early programmers in the 1950s and 60s. But hordes of young testosterone-driven men cannot be relied upon to invent their own disciplines. Process must be given to them from above. And it was fortunate for the industry that right at that moment, 1970, someone wrote a paper. His name was Winston Royce. The paper was called The Development of Large-Scale Software Systems. And the first page of that paper had this diagram on it. And everybody looked at that diagram and said, yes, that's what we need. Now, they didn't bother to read the paper, because the paper went on to say, please don't do this. But it doesn't matter, because they just looked at that first page and said, yes, yes, this must be the way. It makes so much sense. We're going to do it this way. And this process got imposed upon the young, testosterone-driven young men like me. And we suffered through it for 30 years. From 1970 until roughly 2000, that was the domain. That was what we were taught to do. Analyze, design, implement. We could never make it work We always blamed ourselves. It's just because we didn't do it right. We didn't do enough analysis. We need to go back and do more analysis, more design. We're getting into code too fast. Over and over, we went around this loop. Until about 2000, when a bunch of us said, you know, maybe this is a bad idea from the start. A guy by the name of Kent Beck did the Extreme Programming book, and Ken Schwaber and Jeff Sutherland did the Scrum book, and people started thinking about, well, maybe there's a better way, and eventually we all met at a place called Snowbird, and we wrote the Agile Manifesto, and all that stuff happened. And the whole Agile revolution kind of turned us around. So now we're not so focused on waterfall, and we've escaped that early problem. But we have another. I told you that there's maybe 100 million programmers in the world. Well, it's only been 73 years. How do you get from 1 in 1945 to 100 million today in 73 years? 74, depending on how you count. What kind of growth curve is that? Is it linear? It's not linear. Must be exponential. Okay. If it's exponential, let's choose a convenient base for the exponent. We're programmers. We'll choose the base of 2. How many powers of 2 get you to 100 million? What power of 2 is 100 million? What is the log base 2 of 100 million? Well, 2 to the 10th is 1,000. So 2 to the 20th is 1,000,000. 2 to the 7th is 128. 27. 27 doublings from 1945 to now. 27 doublings in 74 years. How many years per doubling? 2.5. 2.5. Does the number of programmers in the world double every 2.5 years? The answer to that is probably not, because it probably doubled much faster in the first decade. Because there was one day when Alan Turing was the first programmer, but the next day there were 10. And the day after that were probably 20. Right. So the first decade, it probably doubled much faster than once every 2.5 years. And then it started to slow down. There's very good reason to think now that the number of programmers in the world doubles every 5 years. And I want you to think really carefully about that. The number of programmers in the world doubles every 5 years. Does that meet with your experience? Can you look around and say, no, the number of programmers I know has doubled in the last 5 years? The number of programmers I see in various places or various meetings doubles every 5 years. Why are there all these people in Montreal at a meeting with some guy yelling at them? Right? Must be a lot of programmers in Montreal. Does the number of programmers in the world double every 5 years? And if that's true, and there's very good reason to think it is, then it has a very stark implication. Half the programmers in the world have less than 5 years experience. Half the programmers in the world have less than 5 years experience, and this will always be true as long as we are doubling every 5 years, which leaves our industry in a state of perpetual inexperience. There is no way we can get the right ratio of experienced people to inexperienced people because we're bringing them out of universities way too fast. Now, we got to have the programmers. So we've got this dilemma. It's a dilemma of inexperience. You look around a programming organization, what you see is a bunch of young people. You don't see a lot of old people. And you come to the conclusion that, this must be a young person's game. Only warped, sick old people would stay in this business. They ought to have gone into something else by now, right? Where are all the old people? No, we're all still here. You know, there just weren't very many of us to begin with back then. We're all still here now. This is a problem for us. And this is where we get into the future of programming. Because what's going to happen? The hardware's changed a lot in the last 70 some odd years. The demographics have changed an awful lot in the last several years, last 70 years, but the software hasn't changed all that much. What is software? If statements, while loops, assignment statements. That's about it. Not much more to it. Oh, you could talk about classes if you want to, but classes are just data structures with functions. We've had data structures with functions for a very long time. Software hasn't changed very much. The hardware's changed a hell of a lot. Software hasn't changed all that much. If I took a programmer from 1968 and brought him forward in time, they'd be able to write the code. They'd look at Java and go, whoa, that's kind of cool. I can write that. If I took you and put you back into 1968, you would be very disappointed, but you could write the code. And you wouldn't find it all that different. The machines you'd find very different. The code you wouldn't find very different. The code hasn't changed much. The hardware changed a lot. But something else needs to change. Our industry needs to grow up. What we are is not a profession. You'd like to think of yourself as a professional, but can you tell me what you profess? A professional professes. What do they profess? They profess standards and ethics and discipline. This goes back to Turing again, the appropriate discipline. What are your disciplines? Can you state your disciplines? Can you outline them and justify them to me? Do you have something you profess, or do you just write code? And the answer is most people just write code. They don't have any built-in standards. They never learned them at school. The school doesn't teach you any ethics of programming, doesn't teach you any discipline of programming, doesn't teach you what the standards are. What are our standards? What oath do we as programmers take to serve our society? And the answer is none. None. People just hire us to do whatever. How much software is running in this room at the moment? 30 years ago, that number would have been none. Today, how much software is running in this room at the moment, sitting on your belt? You know, how much software is running in this thing right now? I got all kinds of processes running in here. Facebook's running in here, and Twitter is running in here, and phone software is running in here, and map software is running in here. As I move it, it is clicking at me because it's thinking that I want its attention. It's telling me that people are trying to talk to me. It's sending me little messages. If a flood occurs in my basement, I will get an alarm here. If the power goes off in my home, I will get an alarm here. This is constantly running. I have software running on my belt, enormous amounts of software. I have software running in my earphones. I put them in my ears. There's a Bluetooth connection to the phone. Little processors are running in here with enormous amounts of software. I've got software in my car keys. My car keys have software running in them. There's software running in my watch. I am a skeleton surrounded by software. The meat of my bones is software. How much software is running in the walls of the room? Is there software in that funny little box on the back wall there? I don't know what it is. Maybe it's a thermostat. Just a little box. Software running in that? I'd give odds there is. That projector clearly has software in it. What about those speakers? Those speakers have software running in them? It's cheaper nowadays, to filter out 60-cycle hum with a little digital signal processor, right? Probably software running. How about the exit sign? Does that exit sign have software running in it? The thing that says sortie, exit, right? I don't know how you say sortie, so I'll just say sortie. Fine. Is there software running in that sign? There's a battery in that sign. Batteries have to be trickle charged to keep the memory effect down. Probably a little digital signal processor in that battery monitoring the charge of that battery. A little fire alarm on the wall. Software running in that? Hope not. How about that thing on the wall there? Well, it's got, it's some kind of touch panel display. Looks pretty complicated. Got to be software in that. There's software running in the walls. And if you go to your house, there's software running in the walls of your house. How much software is running on the roads? Modern car has 100 million lines of code in it. That's not a Tesla. That's just a regular old car. And most of that code is in the entertainment system and the GPS system. But some of that code sits between you and the controls of the car. You realize there's an if statement between you and the brake? Wouldn't you like to know what that if statement says? If what? Huh? How many people have been killed because that if statement failed? The answer to that is dozens. Dozens of people have died because the software controlling the brakes and the accelerator failed horribly. Toyota's paid out a couple of problems with that. What other problems have we had? Who knows about Knight Capital? Knight Capital. Yeah, I won't tell you the whole story. It was just, let me tell you, it's $450 million were lost in 45 minutes because some software idiot did something stupid. Wasn't even that stupid. Right? Just forgot to load one server. Loaded all the other 13, forgot to load one. $450 million. Right? Big loss. How about 737 MAX? Now, that's a pretty bad one. Not all software. There's a hardware component and a software component, but there's definitely a software component in there. You and I are killing people. Now, we did not get into this business to kill people. You know, we got into this business because we went into a store and saw a TRS-80 or a Commodore, and we wrote a little program in BASIC to print our name in an infinite loop and thought we were gods. And now, we're killing people. That's the problem. How often do people in this country interact with a software system? And the answer to that is continuously, on a minute-by-minute basis, because there's nothing you can do in our society without interacting with the software system. You can't microwave a popcorn. You can't wash the dishes or wash your clothes or use the dryer. You can't change the heat in your house. You can't make a phone call. You can't drive anywhere. You can't buy anything. You can't sell anything. You can't pass a law. You can't enforce a law. No insurance can be claimed or filed. Nothing happens in our society unless software sits right smack in the middle of it. Every activity of modern society is governed by software somehow, some way. You and I write that code. We rule the world. Other people think they rule the world. Then they hand the rules to us. And we write the rules that execute the machines that do everything. I think we should talk about our tax rate. That's what I think. We rule the world. We ought to be able to tell people, you know, our tax rate should be different. Otherwise, well, we can make it different anyway. That's it. The day will come when some poor software idiot does something stupid and kills 10,000 people at a shot. It doesn't even take much imagination nowadays to think what that might be. 10,000 people dead one shot just because some software person did something stupid. And when that happens, the politicians of the world will rise up, as they certainly should, and they will point their fingers right at us, and they will ask us how we let this happen. And you might think, no, they're not going to point their finger at me because they're going to point it at my boss, they're going to point it at my company. Does anybody remember what happened when the CEO of Volkswagen North America testified before Congress about why the Volkswagen had software in it that cheated the California EPA system? And the senators asked him, how could you have let this happen, sir? And the man said, and I quote, it was just a couple of software developers who did it for whatever reason. And that finger came right down, right? And it should, because it was a couple of software developers who did it, not for whatever reason. They knew exactly why. By the way, those software developers are in jail now, as they should be, because they wrote lying, cheating code. And this is what I talk about ethics, right? Are we going to write lying, cheating code? Are we going to write code that kills people? Are we going to write code that loses fortunes? Are we going to write that kind of code? Or is there some discipline that we can invoke? At some point, those politicians are going to point that finger at us because the event will certainly occur. And when they do, we'd better have a better excuse than, you know, my boss told me it had to be done on Tuesday. That's not a good excuse. And if that's our answer, then the politicians of the world will do what they must. They will legislate. They will tell us what languages we can use and what frameworks we can use and what platforms we can use, what processes we have to follow, what signatures we have to get, what courses we have to pass, what books we have to read, and we'll all end up working for the government, which I would really like to avoid. So how can we avoid that? We can avoid it the way the doctors avoided it. Because the doctors were eventually regulated, but they came up with the rules first. They enforced those rules first. They came up with their own governance system. And they came up with an oath long, long ago, and they came up with a way of enforcing their commitments and their standards and their ethics. And we should do that too. If we did that, then when the politicians of the world pointed at us and said, hey, how'd you let this happen? Because the event will occur. Whether we're disciplined or not, the event will occur. And when it occurs, when the politicians point at us, it would be a very good thing if we could say, this was an accident, but it was not due to our negligence. Here's our disciplines. Here are the standards. Here are the ethics that we followed. Here's how we enforce it. This was not negligence. This was an accident. And if we can say that, we will probably escape the worst of the regulation they will try and put on us. But we could not say that today. Because right now we don't have that discipline. We don't have the ethics. We don't have the standards. We are not a profession. We need to become one. For our own preservation, we need to become one. But we aren't there yet. Oh, that was a happy note, wasn't it? Yeah, let's see. Oh, yes, 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 yes. Toot, toot, toot. I did so many slides that I didn't talk about. That's okay. There we go. There we are. There we are. There we are. Yup. 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 And that's the end. Are there any questions? Sir.
How do you teach to all those young people that take to your project that and at the same time do some work, not just teaching?
So one of the things we have not been very good at in this industry is developing leaders. And I mean, programmers who have enough experience and who then are willing to take the young programmers under their wing and say, this is how you're going to work. And I'm going to be watching over your shoulder like a hawk, and I'm not going to let you commit anything until you have learned to do these things. Is anybody a pilot in here? Anybody ever learn how to fly? Right? Oh, go learn how to fly. Go to an listen, really, go to an airport one day and take a couple of flying lessons, right? And you watch how the instructor treats you. You're not going to do anything unless that instructor tells you it's okay. And you really want that guy sitting right next to you as you land that airplane for the first time, right? And we don't do that. We get them out of school and say, okay, write us a multi-million-dollar billing machine, go. And these guys, what do they know? Bunch of kids. Well, okay, we'll dink it together. Where are the leaders? Where are the people who know? Where are the people who will say, all right, you three, you're with me, you're sitting with me, you're going to do exactly what I tell you to do. You're not going to step out of bounds for the next 2 years. We don't do that, and we need to. Where are the executives who set expectations? Expectations not just that the software will be done on time, but that the software will be done well. Where is that executive who understands that getting it done well is the key to getting it done on time? Any ship captain knows this. Any ship captain understands that the only way you're going to get things done on time in a battle is to do it damn well. But the executives don't treat the organization like a ship that they are captaining, especially not the developers, because they look at the developers, this is this uncontrollable, unconstrained force of nature that they throw meat at and hope to get programs out of. Most of the problem comes from the way we, the older people, treat the younger people. Right? If we took them aside and said, you're gonna behave this way, and you're gonna behave this way until I tell you not to, that would make a big difference. But we don't do it. We don't do it. We sit there and think, well, we're just programmers and so are they. They're equal to us. They're not. They don't know much. And they're in charge of an airplane that they're going to crash into the ground, and you're going to be riding in that airplane. So you might want to sit next to them and help them figure out how to land. Anybody else with a question? Yeah.
I have 2 questions.
Yes, ma'am.
First one, why Uncle Bob?
All right, I'll answer that question. 1986, I was working at a company, and it was a startup, and there was a guy there that was hired, and he gave everybody a nickname. I was Uncle Bob, and he made it the most annoying way he could. Uncle Bob, come here, Uncle Bob, I want this, Uncle Bob said this. It just made me crazy. And I left that company, not because of that, but I left that company and went to another company, and nobody was calling me Uncle Bob. And I thought, wait, Nobody's calling me Uncle Bob. So I made the mistake of putting it in my email signature. And then everybody knew I was Uncle Bob. And I went to a conference a couple of years later and people started pointing at me, Uncle Bob, Uncle Bob. And I thought, oh my God, I've created a monster. And I tried to take it out of my email signature. And when I took it out of my email signature, people emailed me and said, no, put it back, put it back. And I thought, okay, this must be a brand. I guess I deserve it, fine. And I've kept it ever since. That's how it occurred.
Another question. I'm very curious actually why you wrote about you had a slide in 10 or 15, why women didn't really want to continue being that.
Yes?
I'm curious, was the difference about the income and salary difference? Maybe because they went to be nurses or teachers or what the salary of a programmer and a nurse, for example, in that time?
Programmers were already making pretty good money back then. In the 1970s, let's see, what my salary in the early 70s was around $8,400 a year. I was hoping for 10 grand a year. Boy, that was a big mark for me. I wanted to get to 10 grand. And that probably happened in, I don't know, 75 or 74 or something like that. And then, I wanted to be 20 and then I wanted it to be 30. Salaries were going up pretty fast. Of course, it was hyperinflation at the time as well. So I don't know how to separate those two. That was during the high inflation years. You said something interesting. You said women didn't want. I don't know that that's true at all. They weren't there. I don't know why not. I think that's a very deep mystery that people have tried to solve. And I think people have tried to solve it with very simplistic arguments. I don't think those simple arguments work. I just don't know what happened or why. I don't know what the motivations were.
They are more attracted to take care of other people or teachers and nurses or something. Maybe that's why.
Yes, but you can't say that loud because people get fired for saying that. Right? At Google. If you worked at Google and you said that, you'd be fired. Right? So you can't say that, oddly. Anybody else? How can we have...
How can we help on the whole, how to move forward?
How can we help on how to...
You build the craftsmanship. Are the software craftsmanship principle like the genesis of the oath?
Oh, how can you help with... Well, how can you help with the whole professionalism thing, the craftsmanship thing? Okay. Think about it. Think about it as a necessary part of your job. Think about this idea of standards and disciplines and commitments. Someone that is old enough is going to decide for themselves what their initial personal standards are. What are your standards? Have you made that decision? Do you know what your ethics are personally? Do you know what your disciplines are personally? Can you articulate them to yourself? Can you articulate them to someone else? How many of you, for example, are practicing test-driven development? Okay, so there's about, 10% of you. Where are the rest of you on this? Have you thought about that as a discipline? If you are not executing it, why aren't you? Do you have a good reason? Or are you just kind of coasting along saying, I never needed it before? Do you have a set of disciplines that you specifically adopt, a set of standards that you do? Think about that first. Once you get that in your head, seek out like-minded people at user groups like this. Find if there are other people. Maybe you can talk to them and come up with a more comprehensive set of standards and disciplines. And if it's really that good, maybe that will grow. Yes, ma'am.
So how do you fight against people just saying you're a perfectionist?
You say, no, I'm not. Right? So, and the complaint will be made, right? You're gilding the lily. You're just wasting time. You say, no, I'm not. And that's all you really need to say, right? Because you were hired for what you know. You were hired to be the expert. So you have to act like the expert. And if someone challenges you and say, I think you're wasting time with all this testing nonsense. No, I'm not. Well, I think you'd go a lot faster if you didn't write those tests. No, I wouldn't. Well, how do you know? I've tried that. Right? I definitely go slower if I didn't write those tests. Boy, you should see the mess I could make if I didn't write all these tests. No. I'm definitely writing these tests. Well, I don't buy it. Well, you don't have to. I'm the one writing the code. There is a certain attitude of the professional, right? You don't hire a professional and then tell the professional what to do. You hire the professional and then the professional tells you what to do. You go to a doctor. The doctor tells you what you are going to do. Sir, it's time for you to go to the hospital now. Your appendix is about to burst. You don't argue with that. Right? You go to a lawyer because you're being sued. The lawyer tells you what to do. That's how a professional works. If you are professionals, you will be hired to tell your employer how to work. And when they come back and you say, well, I don't believe that. You say, well, you hired me, man. I'm the professional here. If you want to write the code, go ahead. Anybody else? Yeah?
So we talked a lot about young people, about kids that just learn how to program. So in the 80s and the 90s, there was this culture of hackers that was very popular.
Yeah.
And so sometimes it can also be older people that have this hacker culture, and that can be older than us. So how do you share, or how do we share our culture with these people that have different culture, and how do we try to progress?
So the culture issue is a very difficult one. And let me phrase it in slightly different terms. Let's say that you're working at a company and you want to do test-driven development. Maybe there's 3 other people in the company that want to do test-driven development. You think it's a good discipline. But there's 5 others who don't. This is not a stable situation. There's going to be a divorce. They can't stay together. Right? And you might try for a while. Maybe you'll try to convince them. The 2 cultures will collide, and you'll try to convince each other. Maybe you'll even convert 1 or 2. But in the end, there's going to be a divorce. And somebody's going to quit. Somebody's going to leave. Maybe they can stay in the company and go to a different group. Or maybe you just leave the company and go somewhere else. This is what we see happening over and over and over again. People catch a discipline. They want to follow the discipline. They think it's good. They get really frustrated at the company they're working at because nobody else wants to do it. And they bail out. They go to a different company. And there's nothing wrong with that. And by the way, there's plenty of job openings, so it's probably not going to hurt you much. Might actually make an increase in salary.
Part of our job as a programmer is to estimate.
Oh, here we go with estimation. Yes.
So what should be our discipline or attitude when we ask to estimate?
How much time do we have here? Okay, all right, so I can do this relatively quickly. First of all, remember that these are estimates. The word estimate means guess, and the guess is not a very good guess. So you make it very clear that you are not providing any commitments. These are just estimates. Now, they will interpret them as commitments anyway, but that doesn't matter. Second of all, you never give one number. Right? One number is a bad idea. So what you do is you say, okay, you want to know how long it's going to take me to do X? Well, if everything goes perfectly, and I mean perfectly, like, every morning I have the right breakfast cereal, and my coworkers are always polite, and there aren't any stupid meetings, well, then I could get this done in 3 weeks. If things go the way they normally go, it's going to take me more like 8. And if all hell breaks loose like it sometimes does, it's going to take me 30. Now, you give them those 3 numbers, and I exaggerated them slightly, but the technical definition of those 2 numbers is the 5% and 95% lines. Right? And you give them those 3 numbers. They won't like the 3 numbers. They'll tell you, oh, can't you get better than that? Can't you do better than that? Come on, you can do better than that. No. Well, come on, there's got to be some way you can work this through and get me better numbers than that. I mean, you said you could maybe do it in 8 weeks. Why don't you just say you can do it in 8 weeks? No. Can't do it in 8 weeks. Maybe. About 50-50 odds of that. Right? Not sure I'm going to get any better. Oh, come on, you can do better. Will you at least, and here's the kicker, got to watch out for this one, right? Will you at least try? And here's the process going on in your mind now, right? If I say yes, he'll go away. I should say yes, so that he goes away. But you must not say yes, because yes is a lie. Why is it a lie? Because there is no behavior change you will enact because you said you would try. So what you should say instead is, I'm already trying. There is nothing else I can do. The numbers I've just given you are the numbers that I am confident in. It might be 5 days, it might be 30. 5 weeks, 30. I can't remember what I said, but you know what I said. Now, I will refine those estimates every day, every week. I will give you better numbers because I will know more every day, but I can't give you better numbers right now. That's what you have to do. Make sure that everyone understands that you don't know. That's the most important thing to communicate. You don't know, and you don't have a way to find out until you have done more work. And the work you need to do is the work on the project to help you refine those numbers down. The managers don't like that because that puts the risk on them. They want the risk on you, which is perfectly fair. They want to shed the risk. Of course they want to shed the risk. You must not accept that risk because you can't. You can't make the promise. Never promise something you don't know you can do. Never tell them, okay, man, you know, we're going to really pull out all the stops. We'll get it done by Friday when you're not sure you can do it. Because once you say you will do it, you damn well better do it. So you tell them, give them the odds, give them the probability distribution, and let them fight with you, but don't give in on that. It's very hard to do. You know, programmers did not get into this business because we like people, right? We got into this business because we don't want to deal with people. People are complicated. We don't like that. But you have to be able to deal with people on things like this. One more, if there is one more. Yes?
So you mentioned that Agile is the process that is used by disciplined professionals as observed in the wild.
Yes.
And so I figured the idea was to try to standardize that process and to give it to all the new programmers and all the young people.
Yes.
Any thoughts on why that doesn't work?
Well, it sort of does work. The question was, if you didn't hear the question, it was that Agile is the process that was observed to be used by disciplined people in the wild. All right. Agile is observed in the wild. And we invented it, we reinvented it or rediscovered it in order to help communicate to young people. Do I have any idea why this didn't work? Well, it does. It works fine. If you teach young people to do Agile, they'll be happy to do Agile. Anybody remember Karate Kid? Right? Teachers say, student do. Right? And it really is that simple. You know? The teacher says, do Agile, student does Agile. We don't have a lot of teachers teaching that. And there are a lot of people in companies that could teach it but don't. And that was that whole leadership argument I gave before. But if you get a kid out of school and you say, okay, here's how we're going to do this, right? You're going to estimate in points. You're going to work on a 1-week delivery schedule. You're going to write tests. You're going to refactor. You're going to pair program. You're going to program with these guys. I'll tell you how to do that. If you do that, you teach them that, they're going to do it. And, you know, they may never know another way of programming. Nobody taught them. Nobody told them to do it. We tried, you know, we tried to have, anybody gone through an Agile transition? Yeah, Agile transition, how well did that work? You know, we tried a whole bunch of those. They failed horribly, most of them. They succeeded in converting a few people who then quit and went on to other jobs where they could do Agile. But very seldom did we actually transition an organization. That doesn't work all that well, very often. Maybe some of you have had some different experience with that. I think that's enough for me, huh? Probably enough for you too. Thank you all for your attention.